paste every element. So this is kind of reversing the array with kind of steps starting at the end. Great. So another way of reversing the array is, if you want to reverse the array as a whole, just apply -1, which means start from the end and pick every element from the end till the beginning, and the array will be reversed. This element is there, remember that? This is there. Let's change that element. So so A at position, so I want to find out the index where this minus 1200 is located. So idx is equal to a dot index. I guess there is a function index. Yes and no. Index. Oh, there is no index there. Is there an np dot index? Np dot index. I want to find out the index where so index, there is no index function, indices or something. I want an index function. Is there any index function? I want to find out the index where -200 is located. There are several ways, but I want to find one. So for example, let me see whether there is an index function or not, available in NumPy or not. No, it is no longer there, but there is indices function, I guess. So indices, what that does, I guess that does the same job. Let me see. np.indices returns an array representing the indices of a grid. Okay, so I have to give a grid, and then it returns, for example, the indices of all that grid. How can I use that? Well, it becomes difficult. There may be a find function, or how can I locate the index where the -200 is located? How can I do that? Yeah, very difficult. Seems like very difficult. Oh, why don't I, rather than finding out a function, why don't I just play with NumPy? Why not? So let's say a equals -1200. That gives me a Boolean array comparing each and every element with -1200. So the array, the returning array, let me call the index array, or the Boolean array, let's say B. That array is true or false array, or 0 or 1 array. Wherever there is -1200, that index is 1, that value is 1, otherwise it is 0, completely 0. And then what I do is I just multiply that with the np.arrange with saying that a dot size. So whatever the size of a is. So because these are the indices. Okay, then what? That's the pointwise multiplication. Great. So when I will multiply them together, what I will get is what I will get after multiplication. I will get how can I find out? Actually I'm lost here literally. How can I find out the index where so that will give me what? Let's see. What is B now? The B is just an array. B is just an array, and there is this 3 that is located. So how can I find out where is this 3? How can I again, the problem is finding out the index. Okay, that's really a bad thing. Can I call this a dot indices and just give a -1200 and everything just worked out? No, there is an error. Oh, I'm lost here. Literally, I'm lost here. I need to know how to find out the index where this particular element -1200 lies. So that's a question for you as well. I'm also lost. So let's see you in the next video and we first will solve this problem to finding out the index of a particular element or maybe a lot of elements, and then we will continue from there onwards to see more indexing. Okay, great. So hope to see you in the next video by first solving the problem how to find out the index of a particular element in a NumPy array, or maybe more than one elements in a NumPy array, and then we will be practicing more about these slicing examples. Okay, hope to see you in the next video. Okay, let's say this element is there, and let's say we want to locate that element in the array. We want to just know where this element is in the array. So array A has this element. Let me print array A as it is. This array A has this particular element, and we want to know where what is the index of this element inside the array. There are several ways of doing this. One way is to find out that index is simply you call the function argwhere, for example, argwhere A is equal to -1200. And that will return a 2D array, and if you just want any one index, then you return that kind of thing. So if you write this thing, you will get the index exactly of the element that is there. So the index is 3. If you want to change that value, for example, the value should be 3 here. If you want to change that value, what you can do is you can write A idx is equal to 3, and A is reversed to its position wherever it was created. Okay, great. Now let's play with two-dimensional indices. Let's say two-dimensional arrays. Let's say we have A equals np.random rand. Let's say we have 5 by 4 matrix. Let's say a two-dimensional array. Let's round all the values by multiplying them to 10. What it does is, because all the values, this rand function, all the values it generates are the values between 0 and 1. What this multiplied by 10, what it does is it actually scales up all the values to 10, and then round function actually rounds the values to the integers. Now A will be what's the problem? Round method is no longer there. Okay, maybe there is np.round. Maybe that np.round, maybe np.round is there. Yes, np.round. So round function of np. So this A is this array, for example. That's a 5 by 4 array, 5 rows and 4 columns. So let's say I want to access the second row. First of all, let's say I want to access this particular entry. This particular entry is second row and third column, which means the index is 1, 2, because second row means the row first has index 0, row 2 has index 1. Similarly, column 1 has index 0, column 2 has index 1, and column 3 has index 2. So that is what this particular entry is. What if we want to access the whole second row? For example, we want the second row, so that's how you slice. A normal meaning of this is the row should be 1 and the columns all the columns. So that's how you access the whole second row. If you want to, for example, access the whole third row, for example, or whole second column, let's say, that means you say this, okay, the column number second and all the rows, which means the whole second column that is accessed. And that, if you see, that's the whole second column, 6, 4, 2, 10, and 1. That's what the second column is. Further, once you have you can for example access a submatrix. Let's say you want row number 1 to row number 3, not including 3, and then of these rows you want column number 2 to column number 4, let's say. And if you do that, you access the whole submatrix. First it actually picks row number 2 and row number 3, because row number 2 starts from 1, and then of those rows it picks these columns, and you can just pick the submatrix inside. You can do a lot of processing on these matrices. For example, this is matrix A. If you just type A dot transpose, that T is for transpose, the matrix just is taken transpose of it. Further, there is a complete library, linear algebra library in NumPy. For example, if you just import NumPy dot linear algebra as LA, for example, then this linear algebra library in NumPy has a lot of functions: eigenvalues, Cholesky decomposition, computing determinant of a matrix, finding out inverse of a matrix, and whatnot. For example, let's say we have LA dot inverse, and here is np dot random dot rand, let's say some 3 by 3 matrix. So what it returns is, it returns the inverse of this matrix. And this linear algebra library, and there are other libraries as well, but this is one scientific library that maybe most of data science experts who actually want to do research, they might be thinking this linear algebra library that specifies a lot of functions related to these matrices or two-dimensional arrays. So that is there. Okay, so that's about indexing. We can play with these indices a lot if we want. One more thing, just one last thing. Let's say this is our A, and what we want to do is, let's say we want to sort this A with respect to the columns. We want each column to be sorted individually. What we can do is we can call sort function, and we can pass x is equals 0. X is equals 0. That means sort all the columns individually, and the result will be, if you see the result will be every column is sorted individually. If we want to sort, for example, every row individually, we will say, okay, sort x is equals 1, and every row will be sorted individually. And if this is a multi-dimensional array, more than 2 dimensions, then x's can be 2, x's can be 3. So with respect to whatever x's you want your sorting can happen, it can do that. If A is one-dimensional array, then dot sort function without an axis just sorts the one-dimensional array from beginning to the end. And if you want a descending order sort, just sort it first and then reverse it using indexing. Great. I mean, there is a lot to discuss. I'm ending this slicing here. In the next video, I'm going to show you kind of masking, or sometimes called the fancy indexing, that is much more powerful and useful in a lot of different contexts. So hope to see you in the next video with more NumPy indexing. Okay, there is another way of indexing a NumPy array. In the last video we saw we can do slicing notation, for example, start from here, end at here, and stuff like so. There is another way of accessing a NumPy array, as we have an array A, and we can just give an index array inside. For example, let's say A is one-dimensional array, and then we just give 1, 4, 6. That means pick the element at index 1, pick the element at index 4, pick the element at index 6. So this kind of array inside can be a list or an array that is called an index array. And you can just pick the elements that you want to pick. For example, you want to pick all odd elements. You want to pick first element, fifth element, and 17th element. You can just create an index array and pass it and index and access your elements using that index array. That's possible in NumPy array. Further, you can access different elements using a Boolean mask as well. So Boolean array, for example, true, true, false, false. Wherever there is a true, pick that element. Wherever there is a false, don't pick that element, and return the elements that are picked. For example, assuming here that you have an array A, which is one-dimensional array, let's say, assume that has 8 elements, 1, 2, 3, 4, 5, 6, 7, 8 elements. Now you pass a Boolean mask inside, where with obviously 8 elements 8 true or false values. Wherever there is true, so pick the very first value, pick the second value, don't pick the third value, don't pick the fourth value, pick the fifth value, pick the sixth value, pick the seventh value, and don't pick the last value. So that is also possible in NumPy. One thing that is important is if you do this kind of indexing, which is sometimes called masking. If you do that, if you supply an array index or index in a Boolean form, you by default get a copy as compared to slicing. In slicing, you get a view that's a separate copy. You need not to call a dot copy function. It is by default a different copy. And this is a difference between the ordinary slicing that you do. For example, start from 1, go till 50, take a jump of, let's say, 2. If that is your indexing style, that is called a slicing. The return value is a different view having the same memory. However, if you use the array index or the Boolean array called masks, then you get a copy rather than. So which means if you get a new array, you change the elements in the new array using the array indices, you're not getting that change happen to the original array. So that's the difference between slicing and masking. Okay, this kind of Boolean indexing becomes really handy. For example, what if you want to get all the elements that are smaller than 8? One way to do that is just write a and then apply a condition. A is less than 8. Well, a is less than 8 will create a Boolean array, and everywhere where the element is smaller than 8, there will be a true, otherwise it will be a false. Now the inside array is a Boolean array, and you access all the elements with respect to that condition. So it will return all the elements that are smaller than 8. How fancy is that? Further, you can have these conditions in a combined way. There is one difference. There is an AND operator, and there is an AND operator in a different way. So I'm going to discuss the difference of this AND and this AND as well in this video. So let's go to Jupyter Notebook, our friend, and see how can we play with this masks. So let's say A is again np.arrange, let's say 100. That's our A. And what we now do is we access the elements of A. We access, for example, the third element and the fifth element and the sixth element. Let's say we want to do that. And that's our B. Yeah, so that happens, let's say. So what B is this. Something that you need to know is if you change the elements of B now, because that's a copy, let's say -4, that change does not happen in A. That happens in B for sure, but that doesn't happen in A. A does not contain any value that is -4, because using these kind of indices, the array index, by default, the result is a copy rather than a view. Further, let's say you have this A and you want to access all the elements that are smaller than, let's say 40. Access all the elements that are smaller than 40. So that is possible. Now B will contain only the elements that are smaller than 40, all the elements. Wow. Further, if you want to access all the elements that are smaller than 40, and they are bigger than, they are smaller than 40 and they are bigger than 30. Let's say you want to access all the elements that are between 30 and 40. You can just access those elements like so. There is a problem. A.any, A.all. What's the problem here? The truth value of an array with more than one element is ambiguous. Use A.any or A.all. Okay, this A is less than 40 is a Boolean array. A is greater than 40, that's a Boolean array. So what's the problem? Why can't we not use this? Or what's the problem? We should have used that. So use and yeah, I guess we were missing these brackets because it might be confusing this 40 with this A and stuff like so. So use parentheses. Great. Now B contains only the elements that are between 30 and 40. Now one thing, what's the difference between this particular and this symbol and? The difference is this AND, A and D AND operator, it is used when both of the sides of this AND has one is one object and it has one true value, either true or false. And this particular symbol is used when the left side and the right side can be arrays, and each element of that array can be true or false, and so you can think of this AND is used in arrays. However, this is used when both the sides are single objects. So that's the difference. Other variants of AND, I mean, the AND is like this, that these are the same things, but remember the use. This is used for arrays, this is used for single objects. Similarly, there are other symbols like OR, that is used this way, or that is used that way. Similarly, there is a not for arrays is used like this way, and not for otherwise is used like that way. So remember these, the left side kind of symbols, they are used for arrays. The right kind of symbols, they are used for single objects that has true or false values. So this kind of masking is really powerful. Later we will see in Pandas accessing different kind of data with particular kind of conditioning. That becomes really handy if we are comfortable with these kind of indexing, and that's really powerful indexing. Okay, I have told you the difference here between and. I've told you that this is copy rather than a view. So just bear with me some more time on NumPy, and I will tell you some more truths about NumPy, and then we will move towards another package called Pandas. So before Pandas, more NumPy is coming. Hope to see you in the next video. Okay, in the last video we saw masking, which is sometimes called the fancy indexing as well. And here we are going to discuss one more feature of NumPy, which is a very powerful feature called broadcasting. Think, for example, you have an array, let's say 2, 3, a matrix, let's say two-dimensional array, 2, 3, 5, and 9, and you want to add, in every element you want to add a number, let's say 5. So one way to do that is create another array with 5, 5, 5, 5, and just apply this add operator and you are done. Great. But this NumPy allows you to just write, let's say this is array A. NumPy allows you to just do this particular thing, and this 5 is automatically broadcasted to match with the dimensions of its other operand, and the addition happens. You need not to do this explicitly. And this broadcasting is not just one scalar value. For example, if you have one variable, let's say A is this, and you want to add, for example, this particular column, let's say 1, 3, you want to add this particular column in the first column as well as in the second column. But then you need this 1, 3 to be copied again and make a bigger array, and then you do that. Well, broadcasting allows you, if you just write this as A plus 1, 3, it will be automatically broadcasted to match the size of the other operand. Wherever the broadcasting is possible, there are certain rules to know when broadcasting is possible. It is not possible each and every time. For example, if you have this matrix 2, 3, 9, and you have 4, 2, 1, let's say this matrix, and you want, for example, 2, 1, and 6, 2, for example, if you want to do that, the broadcasting may not happen because in this way, if I want to broadcast this structure should be, if this structure is broadcasted to in horizontal way, the two columns will be added and the addition cannot happen. If it expands to a vertical way, still the addition cannot happen. So this here you will get an error because broadcasting cannot happen. But in several cases, when you want to add, for example, a scalar multiplier with a particular thing, wherever possible, this broadcasting is possible. And broadcasting is just it's just a feature of NumPy that allows you to not repeat to match the dimension of the other operand to apply a particular operator. It does it by itself. Great. Next, we see some more important functions to know. One is horizontal stack. That means if you want to concatenate two arrays that can be concatenated together horizontally, you can call hstack function, and that will concatenate the two arrays together and returns another array. Similarly, vstack is if you want to concatenate two arrays vertically, if they can be concatenated vertically. Similarly, there is another powerful function, sort, and there are a lot of other functions. These kind of functions, they are called universal functions, and they are very, very, very powerful, very, very fast. Their implementation is vectorized. Vectorized mean the implementation, the all loop kind of layer is deferred to at the compile time, and the things are really faster when you do a vectorized code. So having said that, it is always recommended to not use explicitly for loops to achieve these kind of results. Whenever a universal function is available, use that, because the efficiency of that universal function will be way more than whatever loop or whatever function you will be writing other than the universal function. So, and by the way, there is another function, concatenate, as well, in which you can specify x's, and it will either act as horizontal stack or either act as vertical stack, depending upon whether the x's value is 0 or 1, whatever. So let's just get comfortable with these three functions just quickly in Jupyter Notebook and see an example of, let's say, broadcasting as well. So let's say we have a function, let's say we have an array A. A is, let's say, np.random.rand. Let's say that is 2 by 3. And then I just multiply this with 10. Remember this thing, and then we just np.round. We just round everything so that it becomes whole in this particular way. Okay, that's A, let's say. So that's our A. That's the, now if we say A plus 3, the 3 will be added everywhere in A, and that happens through broadcasting. Wow. If we do, for example, A plus, for example, np dot arrange, let's say, just 2 values, and then we just reshape it to let's say 2 by 1 matrix. If you do that, then still what will happen is, just apply the parentheses just to show that this should happen first. What will happen is there will be a column that will be added to every column in A, and that again will be happened through the broadcasting. So broadcasting is that powerful. Next, let's see the stack. So let's say this is A. Let's say we have B. That's another array. Let's say np.random.rand. Let's say that new array is 2 by 2. And again, let's say it is multiplied by 10, and np.round, just to avoid the decimal points. Let's say this is B. Now A is 2 by 3 array, B is a 2 by 2 array. If I just concatenate them horizontally, I will get another array which will be 2 by 5. So C equals np dot h stack, horizontal stack, h stack, and I will call these A and B. One thing that you need to know is if you want to call this h stack, horizontal stack, or vertical stack, these arguments A and B that you want to concatenate, you have to give them in a tuple, or you may want to give several values to concatenate together. Maybe you have 10 matrices to concatenate together horizontally. You have to give all these as a tuple inside. Okay, great. Now similarly, we can do a vertical stack if we want, one on top of the other, and we can call a concatenate function as well if we want. Third is a sort function. For example, if you want to use np dot, let's say A is np dot random dot permutation, let's say np dot arrange, let's say the 10 values, let's say that's our A, let's say this is A, and we want to sort this array. Oh, this is already sorted. Why? Is it sorted? No, it is not sorted. 1/4, it is not sorted. Yeah. Let's say we want to sort it. A dot sort. One way of doing that is just call a dot sort and you are done. That's the value of A. Another way, which is sometimes more readable, although exactly the same, is to use a universal function using np dot that thing. That also is the same thing. Now sort by default sorts in ascending order. If you want to sort in descending order, then what you can do is you can sort a dot sort, for example. You do that in ascending order. Then what you do is you just reverse it. -1 and just copy that in A again. Now A will be sorted. Wow. Sorted in descending order. Yeah, great. One more, just to give you one more flavor. If you create an array, for example, np.array of strings, for example, A, B, C, and another string is how are you, and maybe we have another string U785, and maybe we have another string 13ER. Let's say that's a string. That is possible. As long as all the objects have same type, you can create an NP array. Now you might be wondering, what will do this sort function on A, because these are all strings? Well, the answer is it will sort the strings according to the alphabetic order, whatever the alphabetic order is. Whatever string according to the alphabetic order should become first, that will become first, and the other strings, they will just join. Yeah. So yeah. So that's about something that is not the numeric value. Okay, great. There is a few more things to come about NumPy array, and then we will be moving towards Pandas library that is built on top of NumPy array for better processing of data. Hope to see you in the next video. Okay, in the last video, we saw horizontal concatenation, vertical concatenation, sort function. We also saw some broadcasting and stuff like so. Universal functions, it should be speed here. Sorry, it should be speed. Universal functions are really speedy. I always am talking about NumPy. Whenever I start NumPy, I said it is fast, it is fast, it is fast. I never show you how fast that is. So let me give you an example. Let me just create an NumPy array with a lot of numbers, and then just apply an ordinary function. Let's say I want to add all the numbers in this array B. Let's apply an ordinary function that is not in NumPy, and then let's use a universal function .sum and see how speed difference is there. If, for example, we apply a universal function to achieve a particular task, how speedy that universal function is, because the vectorized implementation, as I told you, is much faster. How faster? Let's check that out in Jupyter Notebook. That's a magic command, time it, that will tell us how much time this particular task has taken. And if you run this command, it will call this function again and again several times, and then will report an average value that will be much more stable than just calling once. After that, we will also write our own sum function using loop, and we will see whether that is even closer to a universal function speed or not. Let us just check the speed of universal functions. That will give you a look and feel of how much NumPy implementation is faster. So let's say we have an array, let's say B, np.random.rand, and let's say that array is huge, really huge. Let's say that's the case. Now what we do is let's say we call a function sum. So let's say we call a function sum. That's a built-in function in NumPy. That's a built-in function. That's a built-in function in Python, not a NumPy function. And then let's say we do the same task using NumPy universal function np.sum. That's the same as np.sum is the same as if we write, for example, b.sum. So whether you write b.sum or you use np.sum and b pass as an argument, both these things are roughly the same. So let's run it. It will take a while. It will take a time because okay, the sum function takes 307 milliseconds. That is not a universal function in NumPy. That's Python function. That is not written in NumPy. That is not a vectorized code, nothing. It takes 307 milliseconds to take the sum of the elements of this array. And it does that by applying 7 runs, 7 loops. However, the universal function takes just around 3 milliseconds, 2.7 milliseconds. How are you going to compare this 307 with 3? How much faster you are? Around 100 times you're faster. Yeah. This NumPy is literally faster. NumPy, the universal function, they're faster. Maybe you attempt to know that, okay, this sum function might be too slow. Let me write my own function. To do that, let me define my sum, and my sum just take an argument, let's say something, let's say g, and what it does is for, let's say s equals 0, what it does is for x in g, s plus equals to x, plus equals to x, and then just return s. That's it. That's your function. Let's say you think that this is really a great function. Let's do that. Okay, let's compute the time for this. Time it, my sum, and let's pass the array b and see how faster this is. This is roughly the same as you're calling the sum function, but this np.sum, or the universal function, is way faster, way faster. So use universal functions, avoid for loops, avoid your own functions if the same task can be achieved through universal functions. Whenever possible, avoid loops when you are working with NumPy. That's a serious suggestion. Follow that, because the universal function written in NumPy, they follow the vectorized code. All the interpreted slowness that is deferred to the compilation layer, and the NumPy becomes really faster and shows its power when you are working on large arrays using the universal functions. So I can speak more about NumPy, but I have told you some basics of NumPy, and we end the NumPy here, and from the next video we will be moving towards a very fancy and beautiful kind of package called Pandas to handle data. And by the way, the Pandas library, the Pandas package, completely is built on top of NumPy. Everything that is there in Pandas is built on top of NumPy. So all the indexing and all kind of stuff, slicing and speed, all is there in Pandas that is due to the NumPy. So we will see one more package after Pandas, which is Matplotlib for plotting afterwards. And we'll do a project at the end using scikit-learn as well, just to wrap up all these things together. But for now, I'm ending NumPy here, and in the next video, we will start Pandas. Hope to see you in the next video. Okay, welcome to Pandas, a data science package that is very powerful of handling data, manipulating data, and used a lot in data munging and data cleaning and data pre-processing and whatnot. This Pandas basically is built on top of NumPy, so most of the features of NumPy is also available in Pandas. Let's dive in. This Pandas is a very fancy library, very fancy package that you can handle very large amounts of data in CSV files or in Excel files, wherever the data is located. The missing entries are there. You can handle all the data, you can manipulate all the data, you can prepare all the data in just a few lines of codes using this Pandas package. So let's just start Pandas package. There are two most important objects of Pandas. One is series, another is data frame that we will see later on. There is one more index, but the most important one is, or the useful one is series and data frame. So let's just define, first of all, you need to import Pandas package, import Pandas, and you can rename this as PD. That's That's the most popular renaming, although you can rename it any. And then you just say, okay, pd.series, and then just like a NumPy array, you pass the data that you want, and you can create your own indices. For example, just like dictionary, this A is a key value. This A is a key or index for this 0.25. This B is index for 0.5. C is index for 0.75, and D is index for 1. So you can supply your explicit indices as well. If you do not supply the indices, the default indices are 0, 1, 2, and 3. But you can define your own indices in the way you want. Now, once this data object is created, you can call the data values, and you will find out the values. You can call data.index, and you will find out the indices. Let's see in the Jupyter Notebook, just to get comfortable with Pandas. First of all, import Pandas as PD, maybe, or something else. So okay, that's imported. Maybe we can check what version we are working in. pd.version. The version of Pandas we are working in right now is 0.24.2. Fine, great. So let's create data or whatever variable, let's say A, as pd.series, and there we just give a list of some values, 2, 3, 4, 5. Let's say these are the values, and then we can give index as another list. Let's say the indices are A. Maybe the indices need not to be strings. Anything A, B, C, and let's say the index of 5 is, let's say, D. So now the series object, or the Pandas object series, is created. Series basically handles one-dimensional arrays. Later on we will see data frame handles multi-dimensional arrays, I mean more than one dimensions. Normally, typically two-dimensional arrays, but okay, A dot values. So let's call the values and you will get all the values inside the series. And by the way, this values array that you get, let's check what's the type of that array. What's type of that array? A dot values, what is that thing? That's a NumPy array. Wow. And what's the type of A itself? That will be a Pandas object. Great. So everything inside Pandas, the NumPy is playing all the role inside Pandas. Great. So now let's check the index, A dot index. That's also an NumPy. That's also an array of index type. That's a different. Actually, index is also an object in Pandas. That's an index type object with these kind of indices. We can access, for example, this A, just like we are working with dictionary. For example, A of A, that returns a value. We can change the values. We can add different. We can add more key value pairs. So just think like just think this data just like the dictionary object that we saw. These are the keys and these are the values. And this is one very good way of remembering what the series does and manipulating series the way we want. Okay, we can access A like this. We also can do slicing. Let's say we want to access from A to, let's say, C. Let's say we want to access all these. One difference is when you access like this, in the normal slicing using implicit indices, for example 1, 2, 3, or 0, the final index is not included. But if you access like so, using explicit indices that are there, the final index is also included. So that is one more fancy way of indexing using in this Pandas. Okay, great. That's a series object. By the way, we can create a series object by first creating a dictionary. For example, let's go back to our slides and see this example. Let's create a dictionary, for example, of grades. Let's say we have a lot of students with grade A minus, grade B minus, and let's create that dictionary. Then we can just create a series object or Pandas object by just passing this dictionary inside. we can make another dictionary, for example, and we can make another series object. So one way of defining the series object is just to pass the data as well as index. Another way is to just first create the dictionary and just pass the dictionary variable inside, and the series object will be created. Okay, that was just the introduction to series. We will move on and see more features of Pandas as we explore it more and more in the upcoming videos. Hope to see you in the next video. Okay, let's say we have two different dictionaries. Let's say we have a lot of students, and the A grade is defined to be 4 and the A minus grade defined to be 3.5. The B grade has a number 3. The B minus grade has a number with a numeric value that is 2.5, and similarly B grade has a numeric value, let's say 2. And then we create just a series object using this dictionary. Let's say rather than just the numeric values as GPAs or something like so, let's say A grade also is defined at 85 marks in total. A minus grade is defined at 80 marks in total, and similarly these. And then we create another series object, let's say named with marks, using these pd.series. So let's go to Jupyter Notebook and just play a little with these dictionaries and build the series object. Let's say marks, or let's say grades dictionary equals, let's say A grade is has A grade has number value 4 or GPA value 4. Let's say we have a B grade with GPA value, let's say B is, let's say 3.5. Let's say we have C grade with GPA value, let's say 3, and let's say finally we have D grade with GPA value, let's say 2.5. Let's say that's a dictionary. Okay, what we do now is we create a grades series object, let's say using pd.series, and just pass this grades underscore dict. Now this capital A, capital B, capital C, and capital D, they will act as indices, and this 4, 3.5, 3, and 2.5, they will act like values. So for example, if we call that and just now call grade.values, so we will get, for example, oh, what is that? That just values. Let's say we get this grades.values, and we get all the values that are available. Similarly, if we find grades.index, we will find out A, B, C, and D. Let's define another dictionary, for example, marks dictionary dict, and that is, let's say again the total marks are 85 for the A grade. Let's say for B grade the total marks are, let's say 75. Let's say for C grade the total marks are, let's say 65, and for D grade, let's say the total marks are 55, let's say. So let's say that's another dictionary. Now let's create a series object pd.series let's say marks dictionary. Yeah. So now again we have, if we just write this marks just like so, you will see the marks. A is 85, B is 75, C is 65, D is 55, and all the values, they are integer 64 kind of values. Now we can access, now we can play with this marks. For example, if we just want to access, for example, what are the marks between, let's say, for example, what are the marks given at A? We can access that, we can change that, we can just play like a dictionary. What if we, rather than using the index A, we use, for example, slicing? We want to start from the very beginning, and let's say we want to go to 2. What will happen? Let's see. Yeah, so the slicing is there. For example, if you want, these are explicit indices, A, B, C, D. These are explicit indices, and they are there. For example, if you can slice the data using explicit indices that you are given, or implicit indices that are the default indices. The first value indexed at 0, the second value is indexed at 2, 1, and so on. So you can do that as well. One catch here, for example, that we will see later on, there may be a problem that your explicit indices, they are also numeric, and then you do the slicing like so, then the series object may be confused whether I have to use the explicit indices or implicit indices inside. We will see how to resolve that issue, but by this pandas allowed to use explicit indices as well as the implicit indices. Okay, we were here. Sorry, I just. So yeah, so we were here. So we have created these grades, a series object, this marks as a series object. The series object is good for one-dimensional arrays or data with just one-dimensional list, or dictionary kind of with just one dimensions. Later we will see data frame that actually is actually the extension of, can be look like as an extension of series towards more than one dimension. We may have, for example, two-dimensional arrays or two-dimensional data structures, something like so, and we will be seeing this data frame, which is much more powerful, particularly for reading data from files and manipulating it and stuff like so. We will see that in the next video, data frame, that running form of data frame in the next video. Hope to see you in the next video. Okay, in the last video we were discussing series, and I told you that data frame is basically if the data has if the data is in a form of different columns, for example a record as an array, then you have another record, then you have another record, and each element in that record is a different attribute. So this particular way of two-dimensional data is very well handled using data frame inside pandas rather than series. So but you can make these data frame object using different series objects. For example, you have a grade object, that grades object that we created last time. You have a marks object that we created last time. Let's build a data frame using these two and see what it looks like in Jupyter Notebook. Let's see that. So remember, we have a marks series object, and we have a grades series object. Let's now make grades. Maybe the name is grades. Okay, the name is like grades. Okay, so grades object, this one. Let's make a data frame. Let's say D, or maybe whatever name you want to do, data frame with, again, that data frame can also be defined using a dictionary. Again, now we have, let's say marks is the key for data marks, and grades is the key for data grades. Let's say we define a data frame like so. And now if you see, if we just display this D, we get a very beautiful look and feel of, I mean, this A is the index, A is the explicit index, A at index A, the marks is 85, the grades are 4. At index B, the marks are 75, the grades are 3.5, and so on. That looks like so. Not only that, you can just transpose it like you have transposed the NumPy array, and you will get the flipped variant or the transposed variant if you want. Great. So that's how, and you can have, for example, more dictionaries to concatenate together, and more columns will be added here. And that's what the real data looks like. I mean, it has a lot of columns, which normally are attributes, and each row is basically one record or one sample of the data that you want to work on. So this data frame is really ideal data structure for working with files, having a lot of records, and you want to manipulate that data and stuff like so. So yeah, so one more thing, let's access the D, for example. Let's print D. That's the D. Let's access the values inside D other than no. So what are the values? So the values inside D is completely, again, a two-dimensional array that is completely like so. So for example, if we want to access this particular element 65, that is row number 3 and column number 1, excluding the indices. That's row number 3 and column number 1. So we can access that particular value, D dot values, just assuming that's a two-dimensional NumPy array. Row number 3 is 2, indexed with 2, and column number 1 is indexed with that, and we will be able to access 65. Wow, great. So that is there. There are more things that are available. D dot, for example, columns, D dot columns. Columns, it will give us what are the columns. The columns are marks and grades. There are other properties, and there are other several properties that we need to know. RS, for example, this there we define this as D dot index and stuff like so. Okay, one more thing that you need to know is we right now we have, let's say, D, that is this one, that's the D. Let's say we want to add another column here, we want to add another column here, and that is the name of that column is scaled marks. And the scaled marks are, what if we have computed marks rather than from 100, what if we have computed marks out of 90? What are the scaled marks out of 90? So one way to do that, and very quick way to do that, is just like a dictionary, again like a dictionary. You just add a new key, let's say scaled marks, that's a new key, and the value is simply all the marks column divided by 90. So is that true? No. Divided by 90, if we have just computed all the marks by 90, and then how can we compute the marks from 90? It is, rather than 100, it is from 90. I guess how can we compute the marks from 90?